8.2 is about arithmetic sequences and series, and when this word is used as an adjective to describe the type of sequence or describe the type of series, it's pronounced arithmetic. When it's a noun, it's arithmetic. When you're adding, subtracting, that's arithmetic, right? When it's an adjective describing a type of sequence or series, it's pronounced arithmetic. Here are a couple examples of arithmetic sequences. So here's 1, 4, 7, 10. So notice it goes up by 3 every single time. That pattern stays the same. So add 3, add 3, add 3. This one goes down, but the way we like to think of this in an arithmetic sequence or series is that it's actually, we're adding negative 10, adding negative 10, adding negative 10, okay? And it's important that we think about it as adding all the time because of what we're going to talk about here in a second, okay? So understand that when a sequence goes up or down by the same amount when adding, we call it an arithmetic sequence. If it doesn't go up or down by the same amount every time, it is not an arithmetic sequence. It may be a different type of sequence. It may just be a generic sequence. But in 8.1, we looked at a lot of sort of generic sequences, but not necessarily ones that went up by the same amount or down by the same amount every time. That's what an arithmetic sequence is. So let's look at some definitions of and formulas. Okay. So when we talk about an arithmetic sequence and it going up by the same amount or down by the same amount, we call that amount the common difference, and that's D. Okay. So if notice here, if we start with my first term, then I add that common difference to it to get the second term. All right. And so here's what that would look like. This is the second term here. The third term is I'm adding another D to the first term. So from the first term I add D, then I add D again. That's why it's 2D to get to the third term. The fourth term is take the first term and I'm adding 3 differences. So I add D again, then add another D, etc. So this is a formula for the second term, the third term, the fourth term, the fifth term. Notice that the number of common differences that we multiply by is always 1 less than the term number. So here I add 1D, which is 1 less than the term number. Here I add 2 Ds, which is 1 less than the term number. And that's going to come up here in a second and why that's important. Another way to come up with the common difference, because sometimes you're going to look at it and be like, okay, like on those examples on the other slide, it was pretty easy. They go up by 3, for example. But sometimes you're not going to be able to tell. So if you're not 100% sure on what the common difference is, you just take the predecessor and the term that comes after it and subtract them. So in this case, I take one term higher, subtracted by the term below it. So for example, this may be the 4th term minus the 3rd term, or the 8th term minus the 7th term. So the following term minus the preceding term. That's how you can calculate the common difference if you don't quite see it. And that's going to happen, you're going to need to use this a little more often when you start seeing arithmetic sequences that are a bunch of fractions or a bunch of decimals. When it's a bunch of integers or whole numbers, it's not too bad. But when it's when they're fractions and decimals, you're probably going to want to use this. Okay. And we need to find that common difference D, and you'll see in a second. Right? And here's why. The nth term of a sequence is going to be the first term plus whatever the term is we're looking for, but 1 less than that times D. So that's where I'm going back to this idea. So I take the first term. Since I'm looking for the 4th term, I have to multiply it by 3 D's. 4 minus 1. So if I was looking for the 4th term, I'd have to go 4 minus 1, which is 3 D's. So the number of D's that you multiply by to add to the very first term is always 1 less than the term I'm looking for. And that's what I was alluding to up here when I was talking about noticing how the multiplier is 1 less. It's because of this formula. Okay. And then if we looked at a recursive formula where we're adding the previous number to get the next number, using the previous number to get the next number, what that would look like is so if I'm looking for the nth term, I take the n minus 1th term and I add D to it. Okay. So in other words, if I was looking for the 8th term, I would have to take the 7th term and add d to it. This has to be true for n greater than or equal to 2. Because if n is not greater than or equal to 2, then this number could be 0, and we don't have a 0th term in arithmetic sequences. Okay. So that's a basic arithmetic sequence formula and the notation that you kind of see with it. So let's go through some examples. One of the things you're going to have to decide is if some of these sequences are arithmetic. And if they are, they'll have a common difference all the time. If they are not, they won't. So on this first one, if we look at it, it looks like it's going down 10, going down 10, going down 10, going down 10. So it's consistent. So I'm adding negative 10 every time. So this is arithmetic, and the common difference is negative 10. And that's all you would have to write. And that's what this is saying. If so, identify the common difference. Now this one over here, see, it goes up by 4, then it goes up by 5. So right away I know it's not arithmetic because this one goes up by 4, this one goes up by 5, this one goes up by 6. Okay. While there's a pattern to it and it's a perfectly fine sequence, it is not arithmetic. In order to be arithmetic, that difference, that term that we add, has to be the same every time. Okay. So that's one type of question that you're going to see. Another type of question you're going to see is where it wants the first 5 terms of the arithmetic sequence. The first term is negative 5, the common difference is 4. And then we're also going to write a recursive formula to define that sequence. So essentially, all I have to do here is start with negative 5, add 4 more times to get my 5 terms. So that gives me negative 5, add 4, negative 1, add 4, 3, add 4, 7, add 4, 11. That's it. There's the first 4 terms, first 5 terms. And here's what it looks like nicely. Okay, now we have to write the recursive formula. In order to write the recursive formula, we first want to have the general recursive formula. So it looks like that. So what we need in order to write the recursive formula is we need A1 and we need the common difference. These are going to be a sub n and a sub n minus 1. Those are going to stay the same. So the first term is negative 5. The difference we identified as 4. So that's what this is going to look like. We have to identify the first term when you write the recursive formula. And then the rest of it plus 4, and you have to have that n greater than or equal to 2. And so that's what A would look like. That's what B would look like. Piece of cake. You're going to have to do some problems like that in your homework. This type of problem is finding a specific term of an arithmetic sequence. So if we're looking for the 9th term, here's what we know. We know that the first term is negative 4, and the 22nd term is 164. I do not expect you to try to write all 22 terms of the sequence out, or for that matter, all the terms to find the 9th term. We're going to use some formulas, but the thing that we don't know right now is the common difference, and we're going to be able to figure that out. So what's important is we need to find the common difference, D. If we find that, then remember our formula, a sub 1 plus n minus 1 times D. All I need is D, and we can figure this out. Now, here's how we're going to do this. Since we know that there's 22 terms, and this has to be arithmetic, that the common difference has to be constant. So here's what we're going to do. Okay. Again, this is the formula we're going to use, and we need to plug in. The problem is we don't know what D is, so I can plug 22 in. This is how we're going to. And so what I'm going to do is we're going to plug in what we know for a sub 22, and then we're going to be able to solve for D. See, we know what a sub 22 is, and we know what a sub 1 is, and then we're going to be able to calculate what D is. So I know that a sub 22 is 164. I know that a sub 1 is negative 4, and then I can just simplify this and solve for D. Okay, and then I'll have the common difference, and then once I have the common difference, I can go back in and plug in here to find a sub 9. and I'll be good. So we finished solving. I get 164 equals negative 4 plus 21d, so I'm going to add 4 to both sides and then divide by 21, so the common difference is 8. So on the next slide, what we'll do is find a sub 9. And basically, all we're going to do is plug a sub 9 here, a sub 1, which is negative 4, and since I'm looking for a sub 9, I'm going to plug 9 in for n there. So here's what that looks like. So again, here's where I'm starting. Here's what I know so far. There's the first term. There's my common difference. Now I want to find, I guess we can simplify it all out first, a sub n, and see what that formula is. And so if I distribute this, 8n minus 8, so I get 8n minus 12. So that's the formula, simplified form of a sub n. You could have also just plug the 9 in here and simplified. You're going to get the same answer. That's up to you. Sometimes they'll ask you to find different terms with the one sequence. So that's where using something like this might be a little more helpful, but you'll get the same answer if you use this one too. Okay. So now to find a sub 9, I just plug 9 in, and that's 72 minus 12, which is 60. And if I would have plugged 9 in here, okay, this would have given me 8. 8 times 8 is 64. Negative 4 plus 64 still gives me 60. So either way, whether you plug the 9 in here or plug the 9 in down here and do the simplifying, it's up to you. It's probably easier to just plug it in right there and save you a little bit of time. That's up to you. All right, so that's that type of problem. Now the other way is, okay, here's this crazy sequence. How many terms are there? Notice the 3, what do they call them? Ellipses? 7, 3, negative 1, negative 5, then a bunch of other terms till I finally get to negative 113. So in order to do this, we're looking for n, essentially is what we're looking for. We're looking for n. And there's a couple different ways to do this, but we can figure out the common difference first, and once we have that, we'll be able to figure it out from there. So in this problem, we notice it goes down by 4, so the common difference is negative 4. We know the first term, we know the last term, so then I can actually just solve for n. I use my normal formula. I can plug in everything that I have. The last term is negative 113. What we don't know is what number term it is, but we know it's the last term. So we're going to have to solve for n. We know the first term, and now we know the common difference. So those things in. Last term is negative 113. First term is 7. The common difference is negative 4. I have enough information here to solve for n. So go ahead and do that and pause the video and see what you get. All right, so we're going to distribute this negative 4. So that's negative 4n plus 4. Combine like terms. 7 plus 4 is 11. Now I'm going to subtract 11, divide by negative 4. Or we're going to flip the sides too, I guess. So 4n equals 124, or if you just subtracted 11, you'd have negative 4n equals negative 124. And divide both sides, and you're going to n equals 31. Okay, so that means there's 31 terms. So again, in this case, we had everything we needed for this formula except n, and that's what the number of terms is. So that's what we needed to solve. We knew the last term, we knew the first term, we figured out the common difference, go through and solve it. The next type of problem you're going to find is they give you 2 terms in the sequence, and you want to find a specific term later on. So in this case, we don't have the first term. So that's kind of important when we don't have the first term. So the first thing that we're going to do is actually find the common difference. And since I have these 2 terms, I can find the common difference since I know that there's 12 terms in between here. And so the way we're going to do that is we're actually going to subtract, almost like it's kind of like the slope formula, right? So if I take 85 minus 49 divided by 27 minus 15, that's going to give me 3. And so if I did this subtraction here, this is 36. This is 12. 36 divided by 12 is 3. So by using these two terms and their indexes and what term they are, we can find the common difference. All I need now is to find the first term, and then I can find the 500th term. So now what you can do in order to find the first term is use one or both of these. I would only use one to find, since I have the common difference now, to find the first term. And I'm going to use this first one because it's first. Okay. So here's where I start. If this is the 15th term, right? The 15th term is 49. And so I take the first term and I add 14 times the common difference. So let me write that in here. So this is really A15. So I'm using my formula. A sub 1 plus 15 minus 1 times D. So that's where this came from. A15 is 49. We're going to solve for this. 15 minus 1 is 14. So now it's just a matter of, we know what the common difference is, right? That's 3. So I can plug 3 in here. And that's 42, subtract, so A sub 1 equals 7. So I have now the first term. I have the common difference. I have everything I need to find the 500th term. So I'm going to use the same formula. So it's going to be A sub 500 equals 7 plus 499D, right? So I have A sub, so this is for if I was trying to find any term. A sub n equals 7, the first term, plus n minus 1 times 3, which is the common difference. In this case, 500 minus 1 is 499, and so that's going to be 1497 plus 7, which should be 1504. Yep. Okay. So again, 499 times 3, which is 1 less than 1500, right? So this is 499 threes instead of 500 threes. So that's where the 1497 comes from. Add 7 to that, 1504. So again, when you're given a situation like this, you have two things that you need to find. You need to find the common difference, then you need to find the first term. And once you do that, you can then find the term that you're looking for. Okay, so that's different versions of arithmetic sequences. Let's talk about series now. So arithmetic series, remember, a series is just adding up the sum of the sequence. And it's going to be true here as well. So talk about it. Let's talk about it. So let's, for example, here's a finite arithmetic sequence, 1, 4, 7, 10, 13. The sum of the first n terms, in this case the first 5 terms, is the nth partial sum, and this is denoted S sub n. Okay? So in this case, all I'm going to really do is add them all up. So the partial sum of the first term is just 1. The partial sum of the first 2 terms, the first 3 terms, the first 4 terms, the first 5 terms. Okay, so it could get a little tedious doing all this adding, but anyway, this is the 5th partial sum, and it's just adding all of those up. This is the 4th partial sum, adding the first 4 up. The 3rd partial sum, adding the first 3 up, etc. Okay, that's what a finite arithmetic series is going to look like. Okay, now let's get into this formula, okay, where the formula comes from. So you don't have to do all this, because I'll be honest with you, adding up a whole bunch of numbers can get kind of tedious. Now, you can always do that, but I'm going to give you a formula that's going to make this a lot easier. So here's where the formula comes from. You don't need to write this down if you don't want to. This is the proof of where the formula that I'm going to show you comes from. I just think it's kind of cool. So if I look at the series of the 5th partial sum, which is this right here, and I just put it in its sort of normal order, that's what it looks like. If I reverse it and put it in descending order instead, it's still the same numbers being added up. Okay, we just add them in a different order. Now, what they do here in terms of the proof is they add those two together. So if I get 2 of those 5th partial sums, notice I get 14, 14, 14, 14, 14. Okay, so this is 5 times 14, right? Because that's the same thing, 5 times 14. And here's why I'm showing you this. Because now to find this, if I just divide by 2, I'll have my answer. Okay? And this is where the formula comes from. So this fifth partial series ends up being 35, which we already knew. Okay? We already knew that. We already knew the answer was 35. But the point is we can use some of our information. Notice here, there was 5 terms, 14. I wonder where that comes from. Well, if I look at the first term and the last term of that sequence, that gives me 14. So what I'm trying to say is we can get from here to here a lot quicker just by taking 1 plus the first term plus the last term, multiply it by the number of terms, and divide it by 2. And that's where our actual formula for a finite arithmetic series is going to come from. Okay, and that's what this looks like. Now, we wrote it a little bit differently. Okay, we wrote it like this: n times a1 plus an, whatever the last term is we're looking for, divided by 2. That's the same thing, right? I could just think of this number being underneath and this group being up top. It's the same idea. Okay, so the nth partial sum of an arithmetic sequence, or an arithmetic series in this case. Take the first term, add it to the nth term, whichever one I'm looking for, multiply that by the number of terms that there are, divide by 2. Okay. So again here, if I go 1 plus 13 is 14, multiply it by the number of terms, there's 5 of them, 70 divided by 2, of course, 35. All right, so let's look at one. Find the sum of the first 50 terms of the sequence. So what I really need is the first term, and I need the 50th term, and I don't have the 50th term, and I certainly don't expect you to write out 50 terms. And this is where our arithmetic sequence formulas come into play, and this is where our arithmetic series formula comes into play. Because once I know the 50th term, okay, I can take, so n is 50, so I've got n, I've got the first term, I'll then have the last term, add those together, multiply by 50, divide by 2, and I'm good. But first we have to find the 50th term, okay? So we need the common difference. We have the first term. We can find the 50th term. So we're going to use what we did for sequences to find the 50th term first. Okay, we're going to use that formula eventually. We need a sub 50 because we know everything else as I just explained. We got to find that. So we got to use the formula for a sub n first, which was this, a sub 1 plus n minus 1 times d. And in this case, we need to find the common difference. Well, it goes up by 2, so the common difference is 2. Okay, I know the first term is 2. So I can simplify this and get my a sub n, or at this point I could plug 50 in too, whichever you want to do. But I'm going to show you how to simplify it so you've got one formula, because in some of these problems, again, they might ask you for a different term number. So I distribute this 2, and I get 2n minus 2, and then, so 2 minus, let me write it out over here. So this is 2 plus 2n minus 2, so the 2's cancel, and I'm just left with 2n. So then all I need to do is plug 50 into that, and I'll have the a sub 50, which of course is 100. So I plug 50 in for n, 2 times n, so the 50th term is actually 100. So I have everything I need now. So using the formula, I've got 50 terms, and then the first term is 2, the second term, or the 50th term is 100. So then I just have to simplify all of that. So the 50th term is 2,550, which essentially this is 25 times 102. And, for that matter, using it like this, 25 times 100 is 2,500, 25 times 2 is 50, 2,500 plus 50 is 2,550. So that's how you'd find the nth partial sum when they don't give you all the terms. Okay, and for that matter, this sequence is an infinite sequence, but they're asking for the first 50 terms. Okay, you could substitute this, pick any number there, and the process would be the same. And once we already have our a sub n formula, then you can find the nth partial sum of that given series. Okay. So there you go. There's 8.2. I know there's a lot there, but it shouldn't be too tough.